Memory is arranged in groups of bytes. That is, remember, one byte is 8 bits. So let's see this representation of a memory. Addresses are noted in hexadecimal numbers. So remember this numbering system and have a look at the different addresses that we have. They're all consecutive, store no more than 8 bits, and um, as you can see, after we reach the number of 9, we start counting 10, 11, 12 by using the first letters of the alphabet. A from F. And in hexadecimal number, this is the maximum value that a single digit can have. So when we reach the number F, we do the carryover to the next digit and there start counting again from 0 in the former digit. That's the carryover that we do when we reach, for instance, 9 in our decimal system. Now let's have a look at this other structure of a memory. Sometimes we have a distribution of memory in which not all consecutive addresses are available for uh, a user program. That is, these positions that we have here may not be available, might not be uh, present or functional, or sometimes they are just reserved for some special functions where it is some other hardware resources or maybe um, any system application of your operating system, so it is not available to be accessed by your applications. That may be the case. In this other um, diagram of a memory, we have exactly the same organization. If you have a look, we have the address 0, and we start counting up to uh, 0, 1, 2, 3, 4, 5, 6, 7. So the next will be 8. And remember, it's hexadecimal numbering system, so this is 8, next one is 9, A, B, C, D, E, F, and then we do the carryover just like in here, F to the next. So it will be um, the, the number 16 in address, but it is written in under hexadecimal numbering. So we can count again this in this digit, that is 10, 11, 12, 13, 14, 15, 16, 17, and then again 18, which is not actually 18, but you know it is the hexadecimal numbering system. What do we have here? As you can see, I purposely merge all of these different bytes, different addresses. You know, all this block is of 8 positions of address. I mean, 8 bytes, alright? So what we have here for the next addresses will be this next one. The first column would be in hex 18, then comes 19 in this position. Then remember that we do pass from the 9 in digit to A, so it will be 1A, 1B, 1C, 1D, 1F, and then we do the carryover to the next digit. So it will become, this digit will become 2, and again, this lower digit will become 0. So uh, all of this block is 8 bytes long, and the final address will be uh, the hexadecimal number 20. And why I'm doing this? Sometimes all of this all of these consecutive addresses may be representing um, a unique chunk of data. What do I mean? Say for instance that it is information about your USB port. So some addresses you need more addresses to store more information. So that's it. That's what I wanted to tell you, because in some diagrams, depending on if you are going to look for a chip or anything else that's not a computer, they also have memory, but larger spaces might be treated under a single logical piece of data. So if we have here the hexadecimal address of 20, the next one in this part will be hexadecimal number 21. Alright? Just wanted to tell you to remember how do we the counting when we are in hexadecimal numbers. So now let's suppose we want to store this data in a particular address in memory. We just transfer this data inside the particular address in memory. But what happens when we have a data this long? We also do the same. I told you that every different address stores only 1 byte. That's 8 bits, alright? But what happens if all of these bits, all of these bytes that we have here are to be interpreted as a single data? What we do is to place them in consecutive positions of memory, consecutive addresses. However, your application, operating system, or whatever software that is treating this piece of data is the one that will be counting in which position what is the beginning and the end in memory. Alright, so it's like the same. It's just stored in consecutive locations because we may need to treat it as a single data piece. However, since memory is arranged in bytes, so we'll have to use consecutive bytes.